So first of all, what we're going to do is we're going to try and look at how we can simplify some complex algebraic fractions and some simple methods for doing it. We're going to start by considering this first expression, x take 5 brackets plus 3 divided by 6 minus 7. Now if we were trying to substitute into that, there's quite a lot of things that we'd be doing. There might be an easier way of doing it. Like the unknown's buried inside a bracket, there's multiple terms involved, division. It's a bit messy. So we're going to focus on this bit here, because adding 7 at the end or subtracting 7 at the end isn't a big deal. It's just this bit here that's a bit yuck. So sometimes it's possible to isolate the unknown. Not quite sure why that's not curly. Let's make it curly. Press that button there. Go over here. Go there. Oh, whoops. That's not good. Make that back into an equation. Press here. There we go. Nice and curly again. So, if we just look at this part and see if we can simplify that somehow, we can definitely simplify the numerator. So x take 5 plus 3 is simply x take 2. Negative 5 plus 3 is take 2. And then we might be able to simplify it further by breaking this fraction into two smaller fractions. So we'll end up with x divided by 6 and negative 2 divided by 6. Now, we know that this negative can be done to plus minus, so we have plus negative 2 on 6, but this looks pretty simple. Quite like that. And then we can rewrite the parts. So x on 6 would become 1 on 6x, and 2 on 6 could become negative a third. And in case it's not quite obvious why that's the case, x on 6 becomes 1 on 6 times x on 1. 1 times x is x. 6 times 1 becomes 6. 2 on 6, we look for the highest common factor, which is 2, divide each by 2, and we end up with 1/6 x take a third. Now, another way of thinking about it is we can halve both of these numbers, so we can multiply both of them by a half, which is what I've done here. A half on a half is still 1, so we're not changing the quantity, we're just changing how it's represented. And that will get us to the 1/3 for this part. We use this logic quite a lot, so it's handy to know it, and it's handy to know why it works. So, here we go. Let's look at a more complex case. 4x plus 8 divided by 2 equals 10. What value of x would make the left-hand side equal the right-hand side? Quite difficult by guess and check. But if maybe if we simplified it first, we could use guess and check. We're reaching the limit of what we can do to find an unknown without some additional algebra. So if we split this fraction up, we could have 4x on 2 and 8 on 2. And 4x divided by 2 is just 2x, and 8 divided by 2 is just 4. And then we can look at this and we say, all right, well, 6 and 4 is 10. So 2 times some number to make 6 would be 2 times 3. And therefore, x must be 3. Now, anything harder than that, I'd be looking to using algebraic techniques, because I'm having to think. And I don't really like thinking. I'd much rather the answer to just fall out. Before we go too much further, though, we should probably go into some conventions. And this is one of the things I've changed between the old version of this video and the new one. In this part, I've said, look, we've got two expressions rather than two terms. I normally treat this as a term, but I suppose strictly speaking, it's an expression. So I've got this expression here and this one here. I've got two expressions, that one and that one, on the left-hand side of my equation. The constant visible is 5. We have x and y. The coefficient of x is -1, and the coefficient of y is 3. If we split into two fractions, we'll have one term, -1 on 7x, another term, 3 on 7y on the left-hand side. We have three expressions total, 1, 2, 3, -1/7 x, 3/7 y, and 5 the constant. There are two variables, x and y. The coefficient of x in this case is -1/7, and in the case of y, it's 3 on 7, which is different to the earlier case. Which is why sometimes talking about coefficients can be difficult. So here's a whole heap of cases where I've expanded it out so that we can look at how and why simplification works. So if we have 10a squared on 2a, a squared I can explain it simply this way. If we have a plus a plus a simple way of saying that is we've got 3 lots of a. If we have a times a times a, so we have to be multiplying the same thing by itself, we said that that's a to the power of 3. It's like a quick way of writing it. In the same way that a times a would be a squared or a to the power of 2. So if we have a squared, we can split that back up, expand it into a times a. And we have this a on the bottom, so we can put it underneath one of those a's. And now we have 10 on 2, which is 5, a on a, which is 1, and a, which leaves us just with 5a. And that's our answer. We can forget about writing this time symbol because we're doing algebra. Same with this one. 9 on 3 becomes 3. B on b, 9 times b is still 9b. 3 times b is still 3b. And that will cancel out to be 1, and we'll have 9 on 3, which is simply 3. And that works the same for this one. We have 2 on 4, which is a half. Highest common factor of 2 and 4 is 2. 2 into 2 goes twice. 2 into 4 goes, sorry, 2 into 2 goes once. 4 into 2, 2 into 4 goes twice. Or multiply the top and the bottom by a half. Gives us that. A on 1, 1 on b, multiply it back out, you end up with a on 2b. 12 on 3, a on a, we'll get rid of that. We get left with a squared, so that's 4a squared. 5a on a times b, that just goes for 5b. 15 on 3 is 5, a on a is 1, we get left with an a on the top and a b on the bottom, 3ab. 24 on 4 is 6. There's just a, so that stays on the top. B on b cancels out, c stays on the bottom. 6a on c. And you're starting to see how now our logic is starting to evolve from having to actually think about what we're doing to just knowing where things end up. So 6a on a squared, we've got more a squareds on the bottom, so we're going to end up with an a on the bottom. We've got more b's on the top with the b squared, so we're going to end up with a b on the top. 2b on a, there it is there. 4 on 2 is 2, a to 7 on a to the 3, a3 on a3 will leave us with a4 on the top, so that'll be 2a to the power of 4. 16 on 2 is 8, b5 on b2, we're going to have b3 on the top, there it is there. 2a to the power 9 on 10a squared, we're going to end up with a7 on the top and a 5 on the bottom, there it is there. 5, a to the power 6 on 2a, we're going to end up with 5 a to the power 5 on the top. One of them will be used up with the a on a, and then we'll have 2 on the bottom. There's 5a to the power 5 on 2. 25 on 5 is 5, there it is there. There's no a's on the bottom, so this a on top will stay there. b7 on b squared, that'll end up with b5 on the top, so 5ab to the 5th. 14 on 2 will be 7, a to the 4 on a to the 3 will leave an a on the top, b to the 8 on b to the 6 will leave b squared on the top. We'll end up with 7ab squared. 9 on 3 is 3, a on a squared will have an a on the bottom, b to the 5 on b to the 3 will have b squared on the top, 3b squared on a, there it is there. 15 on 25, highest common factor is 5, will have a 3 on the top and a 5 on the bottom. A to the 4 on a to the 2 will have an a squared on the top, b on b squared will have a b on the bottom, so that'll be 3a squared on 5b. And there we go. Once we get this idea, it's something that we carry for a long time, and it certainly makes solving equations later a lot easier if we're good at this. Thanks everyone, I'll speak to you soon. Bye.